uh, introduce Professor Katie Bouman. She's a professor in the computing and mathematical sciences and double E and astronomy. I think she has a lot of joint affiliation at Caltech. And before Caltech, she was a fellow, a postdoc fellow at Harvard, and she received PhD, as many of the audience know, at MIT. And she also had a bachelor's degree from Michigan. She won a lot of recognitions and prizes, including Rosenberg Scholar, Heritage Medical Research Institute Investigator, and co-recipient of the Breakthrough Prize in Fundamental Physics, and for Event Horizon Telescope collaboration, which is related to her title of the talk today. She's a co-lead of the imaging working group and acted as a coordinator for papers concerning the first imaging of the M87 and I don't know how to pronounce it.
J star, yeah.
A black holes. Without further ado, let us welcome Professor Bouman.
Well, thank you so much, and thanks so much for the invitation. It seems like a really great seminar series with a lot of great speakers, so I'm honored that you've invited me today. So yeah, I'm going to talk a little bit about the first portrait of our Milky Way's black hole, and actually beyond that, what we're kind of going towards in the future. But before I talk about black hole imaging and what we've kind of done in that space, I first want to just talk about imaging the invisible. So many things that we want to take pictures of are actually invisible to us. For instance, we can't take a picture of our brain using a standard camera. And in these cases, it's impossible to directly image what we want to see. And so we have to develop alternative ways to take indirect measurements. For instance, like using an MRI scanner. And in these cases, the measurements that we make don't look anything like the image that we're trying to capture. And so we have to design algorithms that work with the new sensing system in order to recover the desired picture. And this isn't just true in medical imaging, as I'm sure you know, but in a range of many different applications, ranging from civil engineering to seismic imaging, a field that is referred to as computational imaging. And as just an example, using this methodology, my group at Caltech has worked on problems such as developing techniques to estimate objects' material properties or look at, recover what the Earth looks like beneath the surface, improve medical imaging acquisition, problems like these. But today I'm going to talk about how we've used the same methodology, the synergy between hardware and software that was kind of optimized together to reveal what I think of as being the ultimate invisible. And to me, that's black holes. So if you go out past the bright city lights tonight, you may be lucky enough to see a stunning view of the Milky Way galaxy. And if we could travel past millions of stars, 27,000 light years towards the heart of the spiraling Milky Way, we'd eventually reach a cluster of stars that's right at the center. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the path of this cluster of stars over decades, and what they see is quite remarkable. As the stars come really close to the galactic center, they get whipped around by some like massive but unseen object that's just sitting there. And by tracking the motions of the stars over time, astronomers have concluded that laying within the orbits of these stars must be a compact object with a mass equivalent to 4 million of our suns. And in fact, this discovery led to the Nobel Prize in Physics given in 2020 for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy. And so for many years, people have believed that this compact object is likely to be a black hole. An object that is like so dense that its gravitational pull is going to suck up anything that ventures too close, even light. But at the distance these stars are orbiting, we really can't say for sure. And so in order to study this compact object and to see if it's a black hole, you have to zoom in 1,000 times closer. And there, Einstein's theory of general relativity makes some really exciting predictions for what we should see. So light propagating near a black hole doesn't actually follow straight lines. It's curved because the black hole is curving space-time. And so photons can even go in complete circles around it. So if this compact object actually was a black hole, then the space around it would be lit up by this hot gas spinning around. It's heated to hundreds of billions of degrees, and you have all these photons flying around everywhere. And some that are too close or are pointed in towards it fall into the black hole. But the other photons that are just bent by the gravitational pull, such that the net effect is the black hole casts a shadow on the bright surrounding emission that's almost perfectly circular. So we call this the black hole shadow, which is basically the imprint of the black hole. But this ring isn't going to just take on any size and shape. If Einstein was right about general relativity, its size and shape would be directly related to the mass and the spin of the underlying black hole. And so if astronomers were right about that 4 million solar mass compact object being a black hole, then we should see a ring of 50 microarcseconds, and we wouldn't have a lot of wiggle room because we really are quite sure about that 4 million solar mass number. So we really expect it to be right about 50 microarcseconds. And after many decades of studying this mysterious object, just a few months ago, back in May, we revealed the very first image of this massive body, an image that lined up perfectly with predictions from observations and theory. And so this here is the first ever picture of the black hole at the heart of our own Milky Way galaxy, a radio source called Sagittarius A star, or we like to call it Sag-A star for short. And taking this picture took an Earth-sized telescope with an Earth-sized team. And I'll get into what I mean by that. But first, like, what makes taking this picture so difficult? Well, the fundamental challenge is one of scale. Because the Sag-A star black hole is so massive, it occupies a size roughly the size of Mercury's orbit. And that may sound large, but at a distance of 27,000 light years away from us, that's like trying to photograph a single grain of sand in New York City, but all the way from where I am in the Los Angeles area. So taking a picture of something that's that small actually required this international collaboration of scientists from all around the world, building new instruments and algorithms to make it possible. And as I was talking about before starting the talk, actually there were a number of Korean collaborators also in this, including I want to highlight Il-jae Chow, who really was quite fundamental in a lot of the work that we did here. And so today I want to tell you like a very abridged story of how we were able to take a picture of this black hole. But at this point, you may be saying to yourself, wait, I'm really feeling quite a lot of deja vu. You know, did I hear this story before? It kind of seems kind of familiar. And if I turn this image around, it looks a lot like another image you may have seen a few years back. And this image here, though, is the very first image of a black hole ever produced, which our same collaboration published back in 2019. But this image is actually not a picture of the black hole in the center of our Milky Way, but instead a galaxy that's 55 million light years from Earth called M87. And you might think Sag-A star and M87 look eerily similar, but actually that's no coincidence. That's actually predicted from Einstein's theory. But as I said, we published this image of Sag-A star just a few months ago, and the M87 black hole image was published over 3 years ago. Yet these images were actually recovered from data that was collected in the very same week of 2017. So today I hope to not just answer, how did we take an image of the M87 and Sag-A star black holes, but also what made imaging Sag-A stars so much more challenging. And what we'll learn along the way will also lead to two projects that I want to tell you about today. Two methods that are currently being developed in my group at Caltech to push the imaging of black holes past current limits to see things that are still invisible to us. And in particular, I'll be talking today about new machine learning approaches my group is developing for doing uncertainty quantification of images, as well as how we're developing approaches to recover the dynamics of a black hole over the course of a night, actually in 3 dimensions. Okay, so let's get started. So again, Why is taking that picture of a black hole so difficult? Well, because the black hole shadow ring is so small and can be only seen at a particular wavelength, then diffraction limits, if you remember diffraction, from high school physics, you can plug it into the diffraction limit equation. And it turns out that in order to image something that's that small, that wavelength, we need to build a telescope 13 million meters in size in order to see that event horizon scale structure. 13 million meters is essentially the size of the Earth. And so although we couldn't build a single dish telescope the size of the Earth, instead, the Event Horizon Telescope collaboration spent well over a decade joining telescopes located around the world to build a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. So how does this computational telescope work? Well, the EHT, or the Event Horizon Telescope, we like to call it the EHT, doesn't work like a regular telescope. Instead, the radio telescopes work in pairs, with each pair contributing a little bit of information to the entire image. Telescopes that are far apart detect the smallest and sharpest features. Orientation is also important, with each angle picking up different parts of that whole. And with enough samples, you can recover all the sharpest features. But to get the broader features, you need to bring the telescopes closer together, and combine these components of the image can provide a good representation of the target being observed. So in order to see all the scales and everything of the image, you need telescopes everywhere. And so making a perfect image would require telescopes at all orientations and separations. But the EHT's 8 telescopes scattered around the globe only measure some of these possible pairings. And I want to highlight actually too that these measurements, I'll just talk about them in terms of generic measurements, but they're actually related to the Fourier components. So each point that we measure for every pair of telescopes, the projected baseline tells us which spatial frequency of the image we're actually measuring. So it's related to the Fourier transform of the black hole image. So as I mentioned, sorry, going back, we only measure a very few number of these possible pairings that we kind of need to fill up that whole spatial frequency plane. But luckily, as the Earth is rotating, the separation and orientation between the telescopes change, providing more, but still not all the information we need to make a picture. So we fill in more of that measurement plane, but not fully. So how do we make that image then after extracting these measurements? Well, at this point, we have this data, and so we can kind of abstract away the astrophysics of the problem and think of it as just a purely mathematical inverse problem. We have this sparse data, and our challenge is to invert the measurements to find the image that caused it. And if we were given measurements that cover the entire measurement plane, this would be trivial. But since we only see a few samples, there are therefore an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above every telescope across the globe causes our data to be very noisy, and the problem becomes even more ill-posed. But of the images that are consistent with the measured data, there are some images that we consider more likely than others. Thus, our goal becomes to find an image that doesn't just fit the data, but is likely under some sort of model of likely image, so mathematical model of what is a good-looking image, right? And so by injecting preferences for image statistics into the pipeline, we can use this additional information to whittle down from the infinite possibilities to one solution that we think is a likely image that fits the data well. Okay, so now in this like super hand wavy way, I've told you how we can go from these sparse noisy measurements to a single image, but how do we actually kind of write that mathematically? And I just want to show you this. I don't want to like go too much into math, but I want to show you this because it will come in handy later when we're trying to explain some of the other stuff that we've done more recently. So we're trying to solve an optimization problem where we're trying to find the image X here that maximizes the posterior probability conditioned on the observed measurements Y. And by simply rewriting this using Bayes' rule, we can see that maximizing this log posterior probability is equivalent to maximizing the sum over the data likelihood and the log image prior. And so these are just turn out to be kind of like those two terms that we just discussed in the super hand-wavy way, right? The first one being the data fit and the second being the image likelihood. Okay, but note that even if we can develop these methods such as these to recover a single image, we always have to be super cautious. And that's because any imaging method we come up with, whether it's a if it's a regularized maximum likelihood method like this, or a fancy new machine learning method, it's always going to require that we inject some additional information into the problem about what images look like to recover something back in the end. And in the case of the regularized maximum likelihood problem, it's through the prior here highlighted in yellow. And this additional information is always going to bias our final picture. And that's no matter what happens. It's always going to bias it. And for instance, we're going to have potentially, like, we don't want to accidentally have a preference for ring images and then be super happy that we recovered a ring back in the end for the black hole. And so that meant a big question we faced in dealing with the black hole data was not just how to make an image, but how do we verify that what we are reconstructing with our imaging algorithms is actually real, right? And so this was the big problem, not just making an image, but actually verifying what we recover is the real thing in the sky. But actually, nearly everything that I've said thus far holds true for imaging the M87 black hole as well. So before going into how we image Sagittarius star, let me just do a very quick overview of some of the steps we took in imaging the M87 black hole. Okay, so like I said, we have to be super careful when making images. And we therefore tackled the imaging through a multi-step process, a process that took over a year and a half to complete, that included many synthetic data tests, strict blind imaging procedures, and objective learning of imaging parameters. And the first step of this process was actually to evaluate our methods on collections of synthetic data that tested our methods in every which way. And one thing we learned from these tests is that no method is actually perfect. All methods have their biases. And so it's important to try to assess the commonalities and differences between images recovered under different methods. And so with this insight, once we got the data, we didn't just take one method and make a picture, but instead we developed 3 different imaging pipelines. And you can download these pipelines along with the actual M87 data online. So you can download the data, play with it, make your own. Yeah, and you can download it, make your own and everything, and test it out on all the data that we have. And we designed these pipelines originally to have different hyperparameter knobs on them that control modeling and optimization choices used when solving for the best image. So typically these hyperparameters are tuned by a human user. But instead of having a human tune them, we wanted to instead search for the best set of hyperparameter settings to recover different types of source structures and see how those settings then influence the M87 images we recovered. For instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center, and found the best parameters to recover this shape. So here, this beta here is kind of representing the hyperparameters that we found to recover this shape as best we could. And then when transferring these exact parameters onto the real M87 data, we found that although we had tried our hardest to find parameters that recovered a disk with no hole, our algorithm still required us to put a hole there when we used the real data. And by doing this very simple training and testing procedure on many different types of underlying sources, we saw that our methods always preferred this ring shape. And actually that ended up being true no matter the day we observed M87 on or the imaging code we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to actually form the image that we showed everyone back in 2019, 3 years ago, this ring of light surrounding the black hole. It's roughly 40 microarcseconds in size, really, really small, and brighter on the bottom than the top. So our goal here was to try to remove human bias from the final image as much as possible and use simple training data to select hyperparameter modeling choices that we use to get this image. And this prevented us from tweaking parameters too much by hand just to get an image that we wanted in the end. It wasn't just like us tweaking until we got what we kind of wanted. And by doing this, we did see this ring shape here, which was incredibly exciting. But it doesn't really answer the question of what is the uncertainty in this image? You know, how likely was this ring? And did we just get lucky with these parameter choices we made? And so how did we go about doing that? So previously I talked about how we selected one set of parameters, beta, that perform best on synthetic data. But why should there only be like one parameter set that we consider? In fact, by doing large parameter surveys, we found that there are many parameters that actually perform reasonably well on the synthetic data sets. And so instead of just selecting one set of hyperparameters, we instead set a threshold and we said, okay, let's find all the hyperparameters that perform above this threshold on synthetic data. So for example, for one of the imaging pipelines, we ran hundreds of thousands of simulations and found that we had about 1,500 parameters that we thought were acceptable. And then we would apply those parameters onto the real M87 data to see what variations occurred when we made those different hyperparameter choices. So for instance, as I said, we have 1,500 parameter settings. So we now have 1,500 images of M87 for that one survey, and we can look across them for the variations. So in the middle here, we're showing the standard deviation, and that's telling us where we have variations across the images. And you can see that there are some regions there where we have more uncertainty than others. In particular, you can see these knots along the ring, and that's where we have less control based upon the interplay of the point spread function and the size of the structure, basically, that's being reconstructed. But if you actually look at the value of that standard deviation relative to the mean, so if you look at the fractional standard deviation, it turns out we have a lot of certainty, although we might not know the exact pixel value, the intensity value along that ring appears in basically all the images that we reconstructed. But what really changed is all that wispy stuff on the outside. So really that's what you should not, the ring is a very robust feature, incredibly robust, but what is not robust is all that wispy structure. So don't read into that too much. Anyway, okay, so what I want to strongly highlight here is that what we're doing in this case through this different hyperparameter selection and testing and everything is that what we're doing is probing different modeling choices and seeing how those modeling choices affected the results that we got for the M87 data. So in the regularized maximum likelihood problem, we're essentially changing something like our prior term and then seeing how that prior affected our results. And that's definitely something that's quite important to explore because we do have uncertainty in what that prior should be, especially when we're looking at something like a black hole that we've never seen before, right? But it's also important to note that this is not a posterior distribution. It's not directly quantifying uncertainty due to the data under a fixed prior model. So for instance, oftentimes this energy landscape that you're optimizing is really bumpy, and finding a global maximum ends up being a challenge. But even if you're really lucky to solve this optimization problem well, in order to find a global maximum, there's still nothing to say that there isn't another solution there that's almost as good as that we should also be considering. And so this problem with the optimization here actually ends up being a significant challenge, especially for black hole imaging, where the problem is non-convex actually. And so the energy landscape can be super bumpy. And so just to demonstrate that, here's a synthetic example. So here on this example, on the left side here, we have a synthetic image, a fake image of a black hole. And we took this image and we generated fake mock telescope data from it. as if the Event Horizon Telescope were seeing this image on the sky. So now we have fake telescope data, and using that mock data set, we can run our typical regularized maximum likelihood methods on it and see what results we get. And we noticed that every time we ran the method with slightly different initialization, we would recover different results. In some images, the bright spot was in the top right, and in some cases, the bright spot was in the bottom left. And by evaluating the data likelihood, it appeared that actually both modes fit the data really well, and so we couldn't really tell which one is the correct image. And this is not that rare of an occurrence because of all the crazy noise we kind of experience on our measurements. As I mentioned, we have to solve a non-convex optimization problem. It's similar to a phase retrieval problem. And that sometimes does have multiple solutions that we have to consider. And so this is a bit scary, right? Because it means that we had to manually explore the space of possibilities. And if this was real data and we didn't do this, we could be missing out on another image that would lead to a very different scientific interpretation. So for problems like this, it's so important that we have ways to efficiently visualize the space of possibilities. In other words, instead of computing a point estimate, like the regularized maximum likelihood optimization does, we want to be able to sample from the full posterior distribution, that probability of X given Y, the probability of the image given the measurements, in order to visualize that full solution space. And oftentimes, posterior estimation is achieved using sampling methods like Markov chain Monte Carlo. However, the sampling and rejection approach in MCMC can be prohibitively slow and computationally expensive for high-dimensional inverse problems. And so to tackle this, we recently have been developing new methods for efficient posterior exploration by exploiting deep learning machinery for the purpose of visualizing uncertainty. And I'll explain what that means more. So in particular, our goal here is to learn a deep generative model, deep generative neural network here, to approximate the posterior samples of an imaging inverse problem. Okay, let's dive in a little bit and start by just reviewing the deep generative model. You'll see why in a minute. So I'm sure you all are very familiar with the great success of deep generative models in computer vision and machine learning. So what are these generative models? Well, given enough training images, we can train a neural network that takes as input random noise and outputs a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. So why am I telling you about this? Well, these deep neural networks define an implicit distribution over the space of images. And these impressive results that I've showed indicate that these networks allow us to learn very flexible and expressive distributions that capture complex correlations in high-dimensional images. So inspired by these generative models, my former postdoc, Hassan, who is now just starting his professorship at Peking, and I have been developing an approach to sample a posterior distribution using a learned generative neural network. So our goal is to learn the weights phi here of a neural network such that if you pass different random input noise Z to the neural network, out is going to pop a sample from the image reconstruction posterior. Okay, so we put a different noise input, out is going to pop a different posterior sample. And essentially, this neural network's goal is just to learn a mapping from a noise distribution to the target image's posterior distribution. Okay, well, how do we actually go about training a network like this to give us posterior samples? Well, unlike in the case of the bedroom generator or face generators you may have seen, we don't have a training set of images to use. If we did, if we had a training set of samples from the image reconstruction posterior, then we would be done, right? Because then there would be no reason to learn a neural network to generate samples if we already have samples from the posterior. Instead, the only data we have for optimizing the neural network here is that sparse and noisy measurement data, Y, of a single hidden image. So in our approach, which we call deep probabilistic imaging, or DPI for short, instead of using a collection of training images to solve for the neural network, as is typically done in other computer vision problems, we instead found that we could define the loss that is minimized when the weights of the neural network result in a distribution of network-generated images that best matches the true image posterior. So we saw we can, once we optimize this, we can, the network will produce a distribution that best matches the image, true image posterior. And this is done by minimizing some form of divergence. Here we're going to talk in terms of minimizing the KL divergence between these two distributions. And so doing this actually ends up being a very specific type of variational method. I'll talk about that in a second. So in variational methods, we define a simple family of density functions, for instance, Q phi here, visualized by the blue space of possible distributions. And then we solve an optimization problem to find the parameters phi hat that best match the target posterior distribution. But then the question becomes, okay, what should this family of variational distributions be? Traditionally, they were typically pretty simple, so you could solve the necessary integrals by efficiently evaluating probabilities. So oftentimes, simple distribution families like Gaussian distributions would be used. But in deep probabilistic imaging, by using a neural network, we can define a very flexible family of distributions parameterized by phi, the network weights, and this flexible family of distributions can better capture the image posterior distributions that we're interested in targeting. So actually, so as you can see here, compared to here, where we might have a very simple family of distributions, in when we use the neural network, we can get much more flexibility with it. And actually, this optimization problem can also be intuitively derived by extending the regularized maximum likelihood estimation method. So the KL divergence between the neural network's image distribution and that of the true posterior can actually be rewritten as the expected log likelihood plus an entropy term, which is that last term at the end. And that entropy term is going to encourage the distribution to not just collapse to a single solution, but find a variety of solutions. And so that means, in addition to understanding deep probabilistic imaging DPI as a variational inference method, it can also be regarded as just a natural extension to doing uncertainty quantification for regularized maximum likelihood estimation problems. But in order to solve this problem, we actually need our generative model to be efficient in both generating samples and evaluating the likelihood of an arbitrary image. But most normal generative models like GANs or VAEs, generative adversarial networks and variational autoencoders and stuff, are really only good at generating samples, but can't evaluate a sample's likelihood to compute an entropy loss. So in order to accomplish both goals, in DPI, we use an invertible generative model, a normalizing flow network, and this type of network can actually be executed in both directions. And as a result, we can easily generate samples from noise using the forward pass, and then easily compute that entropy loss we need at the end there using the inverse pass. Okay, so how does this actually end up working? Well, let's go back to the black hole example that I introduced earlier. Remember, for the ground truth image on top, there ended up being multiple solutions that the regularized maximum likelihood would converge to when we would reinitialize. And so we tested our deep probabilistic imaging approach on this data set to learn an approximate posterior distribution. And on the bottom right are some samples from the learned neural network. So remember, we learn the weights of the network, then we freeze that and we just pass different noise through the network to see, and we just gather those samples, and I'm showing them there. And so you can see that our learned network, the samples from it, is able to capture a posterior distribution that also indicates there's two modes in our data. And it doesn't require any kind of manual tuning or initialization or anything like that. This just like naturally falls out, which is pretty cool, I think. But perhaps the most interesting is what happens when we actually run it on some real data. And so this is a result we got when we ran the approach on the real M87 black hole data. And what I find really encouraging is that if you compare the standard deviation in the resulting images to the standard deviation we had published earlier, you can see that actually they're quite amazingly similar. Even though these standard deviation maps actually represent slightly different things, they're actually still comparable. And in both uncertainty maps, we have these three regions with the highest uncertainty that seem to match up. And so this was really very exciting to me when I saw this result, because The very first time Ha ran this method on the real M87 data, he got nearly the same result that it took a whole group months to achieve through these grueling parameter surveys. And it only took about 1 hour of training time on a single GPU. And so I'm really excited to be making progress on methods that allow us to better understand our uncertainty in computational imaging systems. And it turns out that we've found that this DPI framework is not just useful for black hole imaging, but very useful for many different types of problems. And here are just a few of the applications we're working on in our group. But for now, let's get back to the black hole. So the image that we published back in 2019, which was actually not just one image from one method, but an average of images from different methods that all pointed to that same asymmetric ring structure. Okay, so that process seemed to work pretty well for M87. So now on to Sagittarius star. But as it turns out, it wasn't that simple. Imaging Sagittarius star was a lot more challenging. Why? Well, even though Einstein's theory of general relativity says that these black holes should act the same, from our perspective on Earth, these black holes are actually very different beasts. Sagittarius star is much closer to us, 27,000 light years, so don't be worried, but it's much closer than M87's black hole, which is at a distance of 55 million light years. And so that means that although these black holes appear about the same size on the sky, the Sagittarius is just a tad larger. If you actually factor in the distance to each of them, then the actual physical size of Sagittarius star is much, much smaller. So Sagittarius star takes up a size smaller than Mercury's orbit, whereas M87 would extend out past Pluto's orbit. And remember that surrounding these black holes is this turbulent hot gas spinning around. This hot gas spiraling around the two black holes moves at roughly the same speed. But where gas takes days to weeks to orbit the larger M87, in the much smaller Sagittarius star, it's going to complete an orbit in mere minutes, just because it's a much smaller distance it has to move around. And so you can see here 2 videos of a simulation of the Sagittarius star and M87 black holes moving at the same clock as we would see from Earth. And you can see that obviously Sagittarius star is way more dynamic. So why is this challenging? Well, that means that as we're collecting data during the Earth's rotation, the material is swirling around the black hole so quickly that Sagittarius star's appearance is changing from minute to minute. So rather than all the measurements we take overnight being captured from the same static image in the sky, as was the case for M87, now for Sagittarius star, every measurement we get is from a different snapshot of a black hole video. And so we can't simply just throw all the measurements into one pot and expect them to point to the same picture in the sky. So now, not only do we have to deal with sparsity and noise, but our algorithm has to incorporate some way to deal with time variability. And again, each of these decisions is going to bias our final picture. So how should we get the range of possible Sagittarius star appearances? So one way that we dealt with it is by developing 4 different imaging pipelines that would survey how the images would change as a function of different imaging settings. And 3 of these pipelines attempted to characterize the epistemic or systematic uncertainty due to the modeling choices, like the image prior or the variability model. And the 4th pipeline had the goal, similar to DPI that I just talked about, deep probabilistic imaging, of estimating the aleatoric or the statistical uncertainty under this one model. But in particular, similar with M87, these first 3 pipelines have different hyperparameter knobs on them that control modeling and optimization choices. And so you can see here that these surveys included parameters that also included things about, like, for instance, the variability model now for Sagittarius star. And so once we had these surveys set up, we surveyed nearly 175,000 different hyperparameters and saw how these imaging choices affected the images we got out at the end. And so once again, we identified a collection of imaging parameters that performed well across the synthetic data. About 10,000 of the 175,000 were selected from the synthetic data, and then we applied them to the real data to see the possible range of Sagittarius star appearances. And so what did we see when we did this? Well, we saw this huge collection of different types of images. Each of these images here is actually consistent with the Event Horizon Telescope data. But as you'll notice, each one is slightly different than one another. So in order to emphasize the common features appearing in most of the images, we then actually average them together to get the picture of the image that I showed at the beginning of this talk and that made the front pages of newspapers and so on and so forth. And here you can see this bright ring that clearly pops out. But it's also important to note that not all the possible images looked alike. In fact, we found we could cluster the recovered images into 4 different categories based on similar visual features. 3 of these categories contain a ring-like feature with only differing brightness around the ring. However, there existed a much smaller 4th cluster that contained a variety of images that did not appear ring-like. What percentage? Well, roughly 98% of them contained rings and 2% were classified as non-rings. So the question you have at this point is, well, now you've shown me that we're able to reconstruct a variety of different structures for Sagittarius star. Is it a ring? You sure only 2% were non-rings. Does that really rule it out as a possibility? And although these non-ring images could not be fully ruled out from the data alone, we went through a number of tests to try to understand what the origin of these non-ring images is. And there were 2 primary reasons why we may be reconstructing non-ring images. The first explanation is that, the true source is just not a ring. And the second is that our algorithms is artificially creating non-rings, even though the true underlying source is a ring. And so we went through literally years of exhaustive tests to try to better understand these questions. I don't have time to go through them, but I'm actually going to highlight, I can come back if you're interested during the Q&A, but I'll just highlight one of them here just for time reasons. Okay, so option 2 was, could it be that our algorithms just create non-rings from rings? And so what we did is we actually selected a black hole simulation that had a lot of the same statistical properties as our real Sagittarius star data. And we said, okay, well, we know that this underlying source has a ring structure, but what happens when we run the same imaging pipelines on it? And when we did this, we saw something that was very, very similar to what we saw in the Sagittarius star data. Most of the times we recovered ring images, even though the exact distribution around that ring could change from image to image, the distribution of brightness. But what was more interesting is that we also reconstructed non-ring images. And those non-ring images occurred a similar percent of the time. Roughly 4 to 5% of the time, we got a non-ring image, where we saw 2% of our Sagittarius star images were non-ring. And so here with the simulation where we know for sure it should be a ring, but because of all that temporal variability and stuff in our data, our algorithms still have a bit of tough time and sometimes reconstruct a non-ring. And so we thought, well, likely this is also what's happening with Sagittarius star. And so from this and many, many tests, literally years of tests that I'm not talking about right now, we concluded that although we can't say anything with absolute certainty, and I believe science is all about error bars in my opinion anyway, the Event Horizon Telescope Sagittarius star data shows compelling evidence for an image that's dominated by a bright ring of emission. And even more exciting than that is that the ring that we recovered had a diameter that perfectly aligned with prior observations in theory. So 2 very different views of the black hole, one relying on the motion of stars and one relying on the bending and capture of light, were perfectly aligned, which was an extraordinary validation of general relativity. But even further than just testing general relativity, we find that by comparing the picture to simulations scientists have made for years, that the image that we've taken is incredibly consistent with a number of those predictions. But there was some surprises. So remember how I said that black hole is evolving over time? Well, we found that the models that computational astrophysicists have developed over time way over predicted the amount of variability that there would be. In fact, our black hole ended up being a lot quieter than we expected. It was still evolving for sure, but just not with as much turbulence as our simulations had predicted. And we could tell this by looking at the statistics of our data. But in order to really study it, we'd really love to be able to actually recover a movie of the black hole. And so how might we do that? Well, remember the data that we used to recover the black hole image was actually had to be taken over an entire night. As the Earth is rotating, we collect different measurements that together were used to make the Sagittarius star image. So could we use this collection of different snapshot measurements to make a black hole movie? Well, we could break up the data into chunks corresponding to different times and try to make an image for each chunk of data in essence, reconstruct a frame, each frame of the black hole movie, but this would leave us with too little data to produce high quality images. And so instead, what we've been doing is developing methods to reconstruct full movies of the black hole evolving over time. But if you thought recovering a static image was a hard ill-posed problem, this ends up being orders of magnitude more challenging because we have the same amount of data, but now we have to solve for the pixels in a full movie rather than just a single frame. And so to get around this, we have to include temporal regularization, where this temporal regularization controls the continuity that we impose from frame to frame. And we can crank up and down that continuity we impose to try to find movies that fit the data, but allow for more variation or less in the recovered movie. And so now with this method in hand, we went to go reconstruct real movies from the Saturday Star data. However, we found that when we went to make movies, we could recover different movies depending on how we would crank that continuity term up or down. And so really these results showed us that while this image of Saturday Star might exhibit interesting and measurable dynamics, our current methods just like can't conclusively determine the evolution of Saturday Star currently. And so as important as it is to continue pushing on the algorithmic approaches like this to squeeze more out of our data, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And so to that end, we've been working on improving the actual event horizon telescope network. In 2017, we observed telescopes with at 6 different locations. And since then, we've been building out our array, add more data, adding telescopes in Greenland, France, Arizona. And then the one I'm most excited about is we're adding a telescope from Caltech Radio Observatory. But imagine, like what we could do if we could add 10 more telescopes. Well, maybe we could actually make that video of the gas falling into the black hole. And so now I'm just starting to reach the last part of my talk, but I did want to highlight one point that I think is really important. And that's that I believe this effort has really concretely highlighted that there exists this two-way street between science and computational algorithms. Many times people in computational fields go to our science friends and ask them what problems they need help solving. And I think this is fantastic and something we should definitely continue doing. But I think magic really happens when we realize that science just doesn't motivate new algorithms, but sometimes algorithms can motivate new science directions as well. And this actually ended up being the case for the work that we did on video reconstruction of the black hole, which has now started to prompt this whole new line of research into adding these telescopes so that we could eventually make a movie of a black hole in the future. And I found this incredibly rewarding. And so before I end, and I know I only have a couple minutes left, but I really want to briefly highlight another project that we're currently working on that I'm really excited about, that I think embodies the spirit of going back and forth between science and algorithm. And so thus far, we've talked about recovering a movie of a black hole evolving on the projected 2D plane that we see from here on Earth. But what if we could actually recover the emission, not in 2 dimensions, but actually in 3D? See bright flares of hot gas spiraling in 3 dimensions around this dark body. And this imaging capability would not just tell us about the dynamics of accretion, but also could reveal the structure of space-time itself close to the black hole. But how do we actually go about seeing these hotspots in 3D? Well, we face 2 big challenges that separates it from regular 3D tomography that we're used to seeing. First is that our rays are no longer straight, but they bend, but we could deal with that. Second and most challenging is that in 3D reconstruction, typically we have views of the object from all different directions. Like in CT, you can imagine that, or in doing regular 3D reconstructions and stuff. But in our case, we only have one viewpoint ever, and we're never going to see another viewpoint in the black hole. We're never going to see the back sides or the sides of it. We're only ever going to get exactly one viewpoint. And so we have this gravitationally lensed 2D projections from one orientation in the sky. And in fact, we have even less than that. We only have these sparse measurements of the 2D projections over time. But recently, we've developed an approach that we just presented at CVPR this past summer, where we're able to show on toy problems that we're able to take these sparse measurements and use it to help constrain a reconstruction of the evolving 3D environment around the black hole. How do we do that? Well, by injecting just a little bit of the expected physics back in, by saying, let's say we trust general relativity, but nothing else. We don't know what it looks like around the black hole, but we believe general relativity is true. And we impose physical constraints that allow us to jump out, and these physical constraints allow us to jump out of the 2D plane into 3D dimensions. So Aviad Levis, who's a postdoc in my group at Caltech, has been taking a lead on this direction, but with our collaborators, Pratul, Andrew, and Ren. And I don't have time to get into the details, but just to give you a rough idea, we take inspiration from the very popular work in computer vision and build this whole end-to-end deep learning network that uses our telescope measurements to train both the emission asymptote zero and the axis of rotation of a physics-inspired flow field. And these are trained jointly. Basically the network is a NERF network, if you've heard of it, these neural radiance fields. And using this network, we've shown that there's promise in using such an idea to recover dynamic flares exhibited by Sagittarius star over short periods of time. And one other thing I want to highlight is that although what we're doing in this analysis requires us to inject some knowledge of physics back into the problem, it still gives us flexibility in what we're recovering. So here in this picture, we're recovering random digits orbiting the black hole, the numbers 0 through 3. And so obviously we don't think that, we're going to have digits rotating around the black hole, but it's showing that we're able to reconstruct something completely surprising. And that could enable future scientific discovery. And so overall, this is super, super early stages, just a proof of concept. But we believe that this work demonstrates promising first steps towards the scientifically important task of recovering 3D dynamics around the black hole. And I'm just very excited for what scientific questions and technique like this would help us answer in the future. So to close though, it's clear, we've learned a lot from the images of Sagittarius star already. But what I got across in the talk today is that we're really just at the beginning. There's still so much more to come. And hopefully one day we'll be able to not just show you a static image of a black hole, but a movie of a black hole as the gas is slowly falling in towards its event horizon, perhaps even in 3 dimensions. But the main mission I hope I got across today is that computational algorithms have played such a huge role in the science we've done. And it's really just the tip of the iceberg for what can be done. And I hope I can leave you with this picture of this two-way street and urge you to come at these problems in both directions as well. And so with that, I want to thank the amazing team of Event Horizon Telescope collaborators that have worked tirelessly over the last few years on this. They're amazing, wonderful to work with. And I also want to highlight and Aviad, Pratul, Andrew, and Ren, who were on the projects that I discussed today as well. Yeah, happy to take any questions. Thanks.
Hey, thanks, Katie. So let's take some questions from the audience. Are there any questions? Maybe while we wait, I have one or two questions. Maybe you may have got this kind of question quite often. How did you actually begin to get interested in this kind of rather unusual problem for computer scientists and electrical engineer at the beginning?
Oh yeah, I started working on this during my PhD a couple years in. I kind of just stumbled across it. My advisor was invited to give a talk on some of his research, and I was looking into finding a new project. And so I tagged along, and I heard a talk from the other group that was presenting on some work, and I just thought it was super cool. Actually, I didn't understand most of what they were saying, but they were like, oh, we make measurements that are like sparse Fourier components, and it felt very similar to a lot of other problems that I had worked on, although it was on this really cool project around black holes. So I just really I fell in love with it, and then but it really started picking up when I started really going and meeting with the astrophysicists once or twice a week and learning from them and working together with them. And so yeah, it was a bit of serendipity, I guess.
I see. Oh, one more rather technical question is that I read your paper, and in order to increase the resolution, I think there's a limit, theoretical limit called the intrinsic maximum resolution. Maybe due to the maximum distance of telescope
yeah.
pair. With that limitation in mind, I was thinking that this can be related to a super resolution problem in machine learning community. I wonder whether kind of deep learning based super resolution can be combined with this, or is it still not kind of useful?
Yeah, good question. So yeah, the maximum resolution that we get. So for every 2 telescopes in our telescope array, we get a single spatial frequency measurement of the image. And so the farther 2 telescopes are, the higher that spatial frequency measurement. So we define the maximum resolution by the maximum distance between the telescopes, the maximum projected distance. So anything more than that is some level of super resolution. Already the methods like regularized maximum likelihood and stuff like that tend to give you some more super resolution. So just because the nature of images and bandwidth and things like that, you get some level of super resolution. So I would say, so we had about we said that our resolution was about a 20 microarcsecond resolution, just based upon the distance between telescopes and stuff. But we could probably reliably get about 10 or 15 microarcseconds where we trust. But you have to be really careful about this. I mean, super resolution, even though it's a thing and you can demonstrate it on data sets and stuff like that, when you're doing science on it and you're trying to come up with scientific conclusions, you have to be really careful about this. So I do think you could achieve, I think that you could reliably achieve about 10 half super resolution factor of 2 potentially. But past then, I think it would be, even that, I think people are skeptical. Scientists would be a little bit skeptical, but past then, I think it's really, you're starting to hallucinate a lot. So it really, yes, you can incorporate it, but it's a question of, do you want to analyze that for scientific purposes as well?
Right.
Yeah.
I think if you use some sort of a generative model, such as like deep generative models, it may get too creative, then the scientists may not like it. Is that kind of
yeah, but I think it's also good to, so we're working on these kind of things and incorporating deep learning as priors and stuff like that. It's definitely something I'm interested in, but you have to, one thing that we have done, or that we've been doing, is we can learn different kind of distributions from different images, apply those different generative models, right, to help do the inverse problem, or we're in the process of doing this, but and then you can see, well, what are the commonalities and differences, right? You don't want to just go with one strong prior. You really want to see that those features appear no matter what the image distribution you use is, because we don't know what a black hole looks like, right? We don't want to make too many assumptions on that. So yeah.
Yeah. Actually, there's one question on the chat board. Can you read the chat board, Katie?
Oh yeah. It says, my question is, during the training of your generative model, how do you for the deep probabilistic imaging work, how do you actually calculate the prior term in the objective function, the reverse KL divergence? Yeah, good question. So here, any prior that we, so here, this was just using your standard kind of, here, I'll find it for you. This is just using your standard kind of regularization you do when you're solving like regularized maximum likelihood problem. So we already, in the regularized maximum likelihood, we have the ability to compute the likelihood term, and we have the ability to compute the prior term. So you could have this be something more complicated, but in this work here, we demonstrated it with just, I think it was either, we demonstrated with just hand design priors, like L1 or sparsity or maximum entropy or total variation, things like this, where you can just compute this directly. So it's not, but we're also trying out some, as I was just saying, machine learning kind of things that you can have, as long as you can exactly compute what that, what the probability is of an image X, you can use it as in this place here, as long as it's differentiable. Did that answer your question?
Yeah, I guess he's saying
Cool,
okay.
thank you.
Are there any questions from the audience? You can write your questions on the chat board, like the other gentleman. Maybe I have one more quick question. You mentioned this EPI. I was wondering, recently there are like a new kind of technologies that emerging that's popular these days. It's like things like in DALI 2, something called diffusion models. I was wondering whether you have considered using that kind of techniques, or is it already being used?
Yeah, no, so all we have to do for all that's required of that neural network that we use to represent the variational distribution is that it's invertible. And actually, diffusion networks are invertible. So actually, this is one thing that I've been asking my student to do to test out the DPI with, instead of a normalizing flow network, to use a diffusion model, which he's been using for other projects. And I think the it's potentially slower to train, but I think the big advantage of it is that you can get very complicated correlations between pixels in high dimensional images. And so I think that I'm hoping that by switching from a normalizing flow network to a diffusion model network, that we would be able to do the same task on much higher images that are even larger in size and stuff. And so, yeah, this is something that, I'm definitely interested in swapping out and seeing the pros and cons of it.
I see. Is there any way to increase the intrinsic maximum resolution? Maybe, there are a lot of space telescopes being deployed these days, like Webb telescope. Or maybe you can install a radio telescope on the moon, something like that.
Good question. To get higher resolution, really we need telescopes farther apart, and we've already maxed out the Earth. We have a telescope at the South Pole and everything. We've kind of maxed that out. So we'd have to go to space in order to get higher resolution. So it's definitely something that has been discussed. We have had multiple workshops even at Caltech, especially because JPL, Jet Propulsion Lab, is here. And which is about all the space kind of stuff, about the possibility of adding telescopes in space. So one thing is, it's not so easy. This is very short radio wavelengths. You have to have a very smooth dish, and it has to be quite large. So the smallest dish we could potentially get away with is a 4-meter dish, and it's not. And we also have to have specialized hardware on it. Like, we have to have an atomic clock and stuff. It's interferometric measurements. You have to be very, very precisely timed and everything. So it's not something like we can leverage a telescope that's already in space. It would actually have to be a new telescope, and technology would have to be developed for that. So one thing, taking a step back, this project actually, as far as physics and astronomy projects go, is fairly cheap, I would say. Because we leveraged telescopes that were previously built for other purposes and put specialized hardware in it. So it's on the order of $100 million, on that order. Whereas putting a single telescope in space, JPL estimates would be about $500 million to $1 billion.
Wow.
So it's a big price jump. So you have to really show what the scientific gain you'd have from that. And maybe there's definitely potential there. But then the question is, well, what orbit do you put that space telescope? If you go too far out, because we're not going to get a constellation of them, it's too much money, right? But so if you can get one space telescope, where do you put it? If you go too far out, you can get really high spatial resolution, but you can't actually make an image. So you could do something like model fitting, but then you really need to trust your model, right? And then if you go too close in, then you're not gaining too much. You can make images, but you're not gaining too much in terms of resolution. So we're try to identify there's different advantages and disadvantages for different orbits. And so this is one thing that we've kind of studied, the pros and cons of different orbits for a space mission in the future. Yeah.
A naive question is that is it invisible in visible spectrum? Is there a reason why you use like this millimeter wave spectrum?
Yeah, we need to use the millimeter in order to pierce through all the galactic dust and gas and stuff like that to get to that ring of light. It actually is we only from, at least from Earth, are able to view it in a band of about 0.8 millimeters to 1.3 millimeter wavelength. So outside of that, if you go too long, actually the gas around the black hole becomes optically thick and we can't see through. And at too short of wavelengths, the galactic dust and stuff stops us. So, so kind of have this sweet spot there. Yeah.
So that's a physics kind of, yeah, constraint. Okay, I understand. Okay, before we finish, are there any other questions from the audience? Okay, I think today's audience is a bit shy. Okay, let's finish. I like to really thank you, Katie, for your valuable time spending your valuable evening time with us. And
yeah,
thanks a lot.
Yeah,
so thanks a lot for your great talk. It's really fun. Thank you.
Thank you. Bye.
Bye. So let's, yeah.